In last time, we already understand the definition on quenching distance, and you will find out the quenching distance will be governed by these two formula for the low turbulent mixtures and the highly turbulent mixtures respectively. And the meaning on quenching distance is very similar to the definition on ignition energy. That means the quenching distance is a minimal dimension for the spark kernel to make the ignition possible. And the minimal ignition energy is required for the ignition of the premixtures, and they have the same meaning but they can be used from the experiment. Actually, I emphasize if you do the measure the electric energy supplied by the spark and the EGL, they will represent the ignition energy. But you can measure the diameter of your fireball, then you can figure out this is the quenching distance, the diameter of your fireball. They show you the same physical meaning. Now, I try to give you some experimental result to emphasize the dependence on the thermal diffusibility and the turbulent intensity on the quenching distance for low turbulent mixtures and highly turbulent mixtures. And those data came from the experimental result from the CHIM experiment in 1982. Here, the first figure that tell you the quenching distance is a function of turbulent intensity shown in the horizontal axis, and also they will change by the different mixing of inerts. Okay, let me explain a little bit. For example, here they give you the two sets of experiment, one for methane fuel, and the other one is for the propane fuel in the right-hand side. Here, we try to look at original because we think about the usual way, the methane or propane mixing well with air, right? Now, inside of the air, nitrogen will be the inert. Then you do the experiment with the methane mixing with the air, then you can see the quenching distance increase with increasing the turbulent intensity for both case of methane and propane. It is quite easier to understand following the previous formula. You can see when you have a larger turbulent intensity, that means those turbulent AD will carry certain amount of thermal energy away from the control body. You want to make it ignition, right? Then if you have a larger turbulent intensity, then the quenching distance increase. That means you need to have a larger fireball to have a successful ignition. The next part, you try to change the inert from the nitrogen to the carbon dioxide. Actually, nitrogen and the carbon dioxide, they have almost the same thermal conductivity, but for the carbon dioxide has a higher, has a smaller species heat. Okay, nitrogen has a larger species heat. That means species heat, and you go back to the formula, species heat exists in the denominator. When you have a small one, the carbon dioxide has a small value, then the quenching distance will be increased, become larger. Then simply say that you can see the line for the carbon dioxide as inert is higher than the line for the nitrogen, okay, for both cases. This is the first part I try to emphasize. From the comparison of carbon dioxide and nitrogen, they have the same thermal conductivity, but nitrogen has a larger species heat, and this make the thermal conductivity, that make the thermal diffusibility smaller. Then the quenching distance will be smaller compared with that for the carbon dioxide as an inert. Okay, now the next step we think about when we change the inert as the helium and the argon, they will show you the different variation for the thermal diffusibility. Let's compare these two cases, helium and argon. Actually, for the helium and argon, both are simple atomic gases, and they tell you they have almost the same species heat, but the thermal conductivity for helium, because it is smaller, okay, has a small molecular weight, is stronger, larger than the thermal conductivity of argon, which means that they have a higher thermal diffusibility. Lambda, the thermal conductivity occurs in the denominator in previous formula, as you see this curve, this formula, right? Then you have a larger thermal conductivity. That means that you will have a larger quenching distance, and you can see the quenching distance for the helium this time is higher than that for the argon for both cases. Okay, and this experimental result give you the idea about the inference coming from the thermal diffusibility and also the turbulent intensity as we described by the formula for the minima dimension or spark kernel, or we call this as a quenching distance. The next figures, they tell you some inference coming from the mixing ratio and also the pressure, okay? The left-hand side tell you we are looking at the low pressure AKPA conditions. Every curve for a different concentration of oxygens, they tell you this is the invert V-shaped curve, right? Invert V-shaped curve tell you, for example, let's look at the pure oxygen case. They tell you there is the higher value for both sides, has a higher quenching distance for left-hand side and right-hand side. Actually, you can figure out the mixing ratio change based on the horizontal axis. They tell you the propane percent of, this is a concentration percent of boron. You can figure out for 100% oxygen near the bottom of this shape, actually, the mixture's condition is very close to the stoichiometric, okay? In this region, actually, they are corresponding very nice, well mixed, you have enough fuel and enough oxygen, easier to be ignited. Now, the quenching distance reached to the minimum value, but for you increase, if you increase the percent of propane or decrease of propane, they will go through the so-called rich side or lean side. Rich side means you have an extra fuel, and the lean side you will have a extra oxygen. For both cases, they do not have the optimal mixing condition. Then the minimal ignition energy or quenching distance will be increased. This is very easier to understand. And for this case, this is a large invert V shape for 100% O2. When you reduce the oxygens, actually they tell you that they have some inert gas involved, right? And then those kinds of inert, typically in this case, it should be the nitrogen. They will absorb heat. Then quenching distance will be increased. The V-shaped curve will shift to the shift upwardly. Shift upwardly means they need to have more energy, or the quenching distance should become larger than the premixture can be ignited. Okay. Now this is a typical curve, and you decrease the oxygen concentration to the normal 21% oxygen in the air. Then the minimum the quenching distance is the highest one in when you compare with these four curves for different oxygen concentration. This kind of behavior can be found for the experiment with the pressure under 35 kPa, a higher pressure compared with 8 kPa. If you pick one of the oxygen concentration, for example, 50, and compare the quenching distance for the 8 kPa and the 35 kPa, you will find out for the higher pressures, actually the quenching distance is reduced. That means that you need to have a smaller ignition energy. That means the premixture is easier to be ignited under higher pressure conditions. In Chen's experiments, they further give you some experimental measurements on the influence coming on the pressure and the oxygen concentration. Actually, they give you the final results for the stagnant mixture and the flowing mixture. They tell you the minimum ignition energy actually is inverse proportion to the pressure, and also inverse to the oxygen, inverse proportion to oxygen concentration to the power of 4 for the stagnant mixture, or to the power of 5 for the flowing mixtures. And you can see those kinds of results can be justified from the data they show in the following figures. Here, how to read these figures. Actually, this is a log scale. The horizontal axis represents the oxygen concentration you have, and a vertical line, now they use the minimal ignition energy to represent the premixture is easier to be ignited or not. Okay, and here they did an experiment with different pressure. Let's look at one of the pressure condition. For example, 100 kPa. You can see for methane or propane, when you increase the oxygen concentration, here is you increase oxygen concentration, then the minimal ignition energy decrease. This is easier to understand, right? You have more oxygen, then the ignition is easier to be achieved. And this is a straight line in the log scale plot. Represent this as when you take the slope of this linear line, then you can have the correlation result with oxygen concentration as shown here. For the stagnant mixtures, the minimal ignition energy is inverse proportion to oxygen concentration to the power of 4. Okay, here this is this whole experiment data actually represent stagnant mixtures. The flow is stagnant without moving or without flowing. Okay, and for both cases, they show you there is the power to the 4th. Okay, inverse the minimal ignition energy is inverse proportion to the power 4 for both cases. Okay. Additionally, you can see the influence coming from the pressure. When you decrease the pressure, then all the minimal ignition energy will shift to the upper part, represent that you need to have a more ignition energy, then you can have the premixture be ignited. Okay, this experiment data actually just give you the idea to think about the relationship described in the previous formula for the stagnant mixtures. For the flowing mixtures, they show you the same results, but the slope for the linear lines are different. Actually, they tell you the minimal ignition energy for both cases, methane and propane, for the flowing mixtures. Actually, the minimal ignition energy is inverse proportion to the order of 5 for this case. That means that it is stronger influenced by the oxygen concentration in the flowing mixtures. Okay, and those kinds of experiments they are just be compared or confirmed and be summarized as these two correlation equations. You can refer it, and from those kinds of experiments from the literatures, and you can justify the formula derived by the ignition theory is suitable to be used to estimate the capability of ignition of a premixture. Okay. Now the next step I emphasize because from the so-called S curve from based on the Danko number, and we understand there is the two so-called transit state. One is ignition. The state of ignition is a function of time. The other one is the transit state. We need to discuss it is the extinction. Okay. Now we move to how to define the so-called extinction. Based on the definition of ignition, you need to supply enough energy of active species into your premixture, then you will start to have a chemical reaction continuously, right? This is a basically for the idea of ignition of your premixture. And you can go back to conversely thinking. Then you think about the flame extinction, you already have a premixed flame, right? And you're right. Now you are thinking about the factor to ignite a fraction mixtures. Now you think about how to quench it. Simply say if you can carry certain amount of energy out, thermal energy out, then this chemical reaction will be turned down, right? This is one way. Or you move away those kinds of active species. The same thing, you will suppress the chemical reaction. which means you can have the idea about the achievement on the extension of a steady burning flame. And there's two methods for you. One is removing the chain carrier of reaction chain radicals. You remove those kinds of OH or O radicals, then you will cut all the chemical reaction step, and they will terminate all the chemical reaction, and the flame will extinction. The similar way, the example is, for example, introducing chemical inhibitants to the reaction zone or placing the flame next to a surface which deactivates the radicals. Introducing chemical inhibitant to the reaction zone, this is simply can be observed from the fire extinguishment. When you have a fire and you use the carbon dioxide inhibitant, or you may use the sand put on the fire, and those kinds of sand or carbon dioxide, they will give you some inhibitants. They will break up or carry out the chain carrier of chain radicals. Then they will terminate those kind of chain reactions. Then the chemical reaction will cease, and you will not have a flame extinction. Okay. The other one, remove the heat. I think the easier way is blowing it with a cold gas or with the cold surface. Even you can, for example, you can introduce the fine inert particle into the flame zone. The simple way is you use water spray. Okay, usually for the firefighter, they use the water to quench all the heat contained in your combustible region, then flame will extinction. This is a typical examples you can see for the extinction of a burning flame. And there is a theory, we call this the flame quenching theory, for the naming premixture by heat loss reported by Spalding in 1957 and Mayer in 1987. And later, Buckmaster and Lafleur, they used the perturbation theory to analyze the flame quenching theory, and they get this kinds. This is very nice theoretical result. They tell you the burning. This is a mass flow rate, or you can see this as the flame speed. Is a function. It's an exponential function of a T1 plus 0. What is the meaning of T1 plus 0? Actually, this is a small temperature perturbation at the flame zone. For example, you have a flame temperature, right, at the flame position. That is the maximum flame temperature, in your flow. But now, when you apply some heat loss, the temperature will be decreased because chemical reaction is weakened, right? And those kinds of variation can be found by the T1 plus 0. Plus means the downstream of your premixed flame, very close to the flame surface. Okay, and this small variation large to a certain amount, then flame will extinction. Okay, by applying this results, they can plot as very famous curve. We call this a so-called C-shaped extinction curve, or we call this a double value function. How to look at this? There's the now you can look at the vertical axis m dot. This is the mass flow rate, or you can see we can look at is a flame speed, flame propagation speed, and a QL represent the heat loss. But this heat loss may come from the conduction loss, radiation loss, combustion loss, different kinds of heat loss get involved. You can have the total amount of heat loss as a quantity, and show in the horizontal axis. And they tell you for given heat loss, you may have, for example, here starting from 0. 0 means you do not have a heat loss. Here, this is an adiabatic case. Now you have 1, because m dot is a non-dimensional quantity. M dot 1 it represents, now you have a propagation velocity. Okay, this is equal to 1. You divide by the flame speed adiabatic case, then this is equal to 1. This is a stable burning 1. Now you try to increase your QL. That means that you increase your heat loss. Now, from the theory, actually, the solution give you this kinds of V-shaped curve, okay, C-shaped curve, inverse C-shaped curve. But from here, they tell you if you look at the upper branch, the frame speed starting from 1 equal to the adiabatic case. Now, because the influence coming from the heat loss, the frame speed will continuously decrease as you increase the QL. Okay, and this curve, the upper branch of a C-shaped extinct curve tell you this is can be justified by experiment that tell you the burning strength, the flame speed continue decrease as you increase the heat loss. At certain point, if heat loss is large enough up to here, later on you can see there is the turning point. Tell you after you increase QL larger than this value, then you will not have a flame. The flame disappear. That means a flame extinction. Okay. The upper branch actually can be justified from the experiment, but lower part, the lower branch actually is not justified. It just occurs from the theoretical analysis. Then people say this the lower branch basically is the unstable solution you cannot justify from the experimental observation. When you look at this curve, I hope you remember there is the similar variation shown by the S curve, right? They just invert the S curve to show starting from the steady burning from the left-hand side and the continuous decrease to the right-hand side. When you go back to the S curve, let's move it a little bit to the previous slides. In the very earlier slides, I hope you have, here is 1.16, right? Can you figure out the so-called C-shaped extinction curve? Just the just the reverse of this intense burning branch. For example, here you can see this is equal to 1, right? If you do the normalization for the adiabatic value is equal to 1, then they are continually, because Dunker number actually they give if you try to change it as a heat loss starting from the right hand side and you continue increase the heat loss, then the burning rate initially they may not have too much change, but later on they will change it decrease to a certain value up to here, then extinction appear. Okay, the C extinction curve actually is the reproduce of the upper branch of the Dunker number plots. They show the same results, okay, the same meaning of the so-called extinction behavior. Now we go back to our C-shaped extinction curve. Okay, here in summary, from these figures, actually this is very famous curves predicted by the extended theory that tell you a given combustor premixture has two possible flame speed for fixed amount of heat loss. From this plot, they tell you for example for 0.2 QL, they may have one solution in the lower branch, the other one in the upper branch. However, the upper and the lower value normally represent a stable and unstable solution respectively. You can have an experimental observation for the stable solution, but you may not have an unstable solution from the experimental observation. Then the extinction limit is identify the turning point. Turning point means after the turning point, you may not have a solution theoretically exist. And from the practical experiment, they tell you you cannot have a flame exist in your premixture. That means the flame is extintional completely in your given flow. And I think I will not go through further because now there is some theory even include my theory published in 1989. We try to introduce some kinds of inert, for example, water or inert that can absorb the heat into your flame zone for the one-dimensional flame. As I mentioned previously, if you try to make the flame extension, make flame extension, and you can bring certain amount of heat out. There is one way you apply water mix, or you use some inert particle into your combustion zone, and those inert or water, they will absorb heat and produce the extension. And those results will get involved with the two-phase flow, and they still have a C-shaped curve, but with the droplet participations, they have some kinds of S-curve occurs, and a triple value function can be formed. I will not describe this too much detail for you because we did not give you the idea about the spray characteristic. Now I finished the introduction on the extension. Actually, I try to emphasize the mechanism for the ignition and extension. Basically, these two, ignition and extensions, are transient states. Okay, all the variation of the burning characteristic for ignition or extension, there is a function of time. But for ignition, actually, the time interval, actually, you do measure. You can measure it. But for extension, up to now, people do not have a very definite conclusion for the time for extension. From our experiment, actually, the extension is always occurs suddenly in a very short time, even you cannot measure. But for the ignition, then you can do the measurement when you supply the electric energy from the spark, and you can count the flame occurs by the microsecond or millisecond, something like that. That means they still have a so-called ignition delay time. Okay, the delay time, the ignition delay time means when you supply thermal energy into your combustible mixtures, then they still need to have a very short time to initiate the chemical reaction, the multi-step chemical reaction. And when they can have those kinds of multi-step chemical reaction in the short time, then ignition will continue to make the flame be self-sustainable, then propagate. Okay, the ignition delay time usually can be described for the ignition experiment, but nobody used the so-called extension delay time. Extension always occur in a sudden way. They do not have a exact measure how long it takes the flame extension. Okay, this is a complete difference. I say the transient state for ignition and extension, but extension is almost extreme fast. Then you even you do not have a chance to measure how long of the how much time they will take to make extension. But anyway, there's still I give you the idea based on the Danko number curve to tell you to think about the increased Danko number. You can make the premixture ignited, and you will reduce the Danko number. The propagating flame will be weakened continuously, then extension. Okay, those kinds of abrupt change by the turning point on the S curve or on the C-shaped curve to represent ignition and extension behavior.